Welcome to episode 3 in the AI Audit exam prep series. Today we are exploring the fundamental building blocks of artificial intelligence. We will break down exactly what algorithms are, how hyperparameters control them, and the distinct classes of supervised, unsupervised, and reinforcement learning. We will also clarify essential terminology like large language models, model fitting, and natural language processing. As an AI auditor, mastering this vocabulary is your primary tool for evaluating enterprise risk. When a business unit proposes a new AI system for predicting financial trends, you must immediately recognize if their chosen mathematical model is actually capable of that specific task, or if it will introduce hidden financial liabilities into your corporate workflow. Let us begin with the core concept of algorithms. At its most basic level, an algorithm is simply a set of step-by-step instructions designed to solve a specific problem or execute a task. Think of it like a blueprint for assembling a bookshelf. You follow the defined steps and you get a usable piece of furniture. In machine learning, algorithms process input data, extract hidden patterns, and make predictions without a programmer having to hard-code rules for every possible scenario. But an algorithm does not operate entirely unchecked. It is governed by settings called hyperparameters. A hyperparameter is a specific configuration that a human engineer adjusts before the training process even begins. If the algorithm is the blueprint for the bookshelf, the hyperparameters are the torque settings on your power drill. You set the dial in advance to control exactly how fast and how deeply the screws are driven. In a corporate AI system, hyperparameters dictate things like the learning rate or how complex a decision tree can grow. As an auditor, you must verify that engineers are actively selecting the right hyperparameters, because incorrect settings will completely derail the learning process and produce highly unreliable predictions. Now we will categorize the specific classes of algorithms, starting with supervised learning. Supervised learning requires labeled training data, meaning the system is given the correct answers up front so it can memorize the clear relationship between inputs and target outputs. There are 4 primary supervised models you need to know for the exam. First is linear regression. This algorithm models the relationship between different variables by fitting a straight mathematical line to observed data points. Imagine trying to predict your morning commute time based entirely on the number of miles you have to drive. Linear regression draws a line proving that as the mileage goes up, the expected travel time smoothly and reliably increases. Second is logistic regression. Do not let the name fool you. This is actually utilized for binary classification. It predicts the absolute probability of an outcome that must fall into one of 2 distinct categories. A real-world example is a corporate firewall, determining if an incoming email is a malicious phishing scam or a safe communication. It provides a strict either-or result. Third, we have tree-based models. These algorithms handle highly complex, non-linear data by creating a branching, hierarchical decision structure. The model recursively splits data based on input variables until it makes a final prediction at the end of a branch, which is called a leaf node. Think of a medical triage questionnaire at a hospital. Are you experiencing chest pain? Yes or no. Are you short of breath? Yes or no. The model branches continuously downward until it isolates the correct patient risk category. Finally, we have support vector machines. These establish a rigid decision boundary, which is mathematically called a hyperplane, to firmly separate different classes of data. Imagine looking at a geographic map showing a lush forest right next to a dry desert. A support vector machine calculates the absolute best place to draw the borderline so that all the trees are distinctly on one side and all the sand is on the other. This method is incredibly robust, even when you only have very small amounts of training data. Next, we transition to unsupervised learning. In this class, the system is fed raw, unlabeled data and must discover hidden structures and similarities entirely on its own. You must fully grasp 3 specific approaches here. The first approach is k-means clustering. This is an exclusive method that groups data into a predefined number of clusters represented by the mathematical variable k. It operates by locating the exact center of each group, known as a centroid. Imagine a retail company dropping a massive database of customer purchase histories into a system, asking it to automatically create 3 distinct marketing tiers. The system does not know the actual names of the customers, but it successfully clusters them into bargain hunters, regular shoppers, and luxury buyers based purely on their spending similarities. The second approach is hierarchical clustering. Instead of flat, isolated groups, this generates a layered tree of clusters. It can work from the bottom up by merging individual data points, which is the agglomerative approach. Or it can work from the top down by dividing one massive cluster into smaller pieces, which is the divisive approach. Think of organizing the workforce of a massive international corporation. You group individual employees into small operational teams, then merge those teams into distinct departments, and finally merge those departments into regional divisions, creating a perfect structural hierarchy. The third approach is principal component analysis. This is an advanced statistical method that simplifies massive datasets by transforming original, overlapping variables into a new set of independent, uncorrelated variables, which are called principal components. The first principal component captures the maximum possible variance in the data. Imagine looking at a gourmet recipe with 100 different, highly obscure ingredients. Principal component analysis mathematically condenses the list down to just the 5 core flavor profiles that actually define the dish, filtering out all the unnecessary complexity. The third major algorithm class is reinforcement learning. This dynamic process relies purely on trial and error, where the system learns over time to maximize a mathematical reward signal. We start with Q-learning. This is a model-free algorithm that learns the expected utility of taking a given action while in a specific state. It updates these numerical values, called Q-values, inside a matrix known as a Q-table. Through endless repetition, it eventually finds the optimal sequence of actions. Imagine a laboratory mouse running through a static physical maze to find cheese. Every dead end updates its internal mental table with a severe penalty, and every step closer to the cheese updates the table with a high reward. But a simple matrix table completely fails when the operation environment is too massive. That is where deep Q networks, or DQNs, step in. Deep Q networks handle high-dimensional spaces by replacing the traditional Q table with a deep neural network. The network takes the current state of the environment as an input and rapidly calculates the Q values for all possible actions simultaneously. If basic Q learning is a mouse in a static, unchanging maze, a deep Q network is a modern robot vacuum, learning to clean an active household where children and pets are constantly moving toys and furniture around in real time. Finally, we have policy-based methods. Instead of calculating a specific numerical value for an action first, these methods directly optimize the policy function itself. They directly learn the mathematical mapping from states to actions. Imagine an experienced professional surfer riding a massive ocean wave. They do not pause to mentally calculate the expected value of shifting their physical weight slightly to the left. They have directly trained their physical policy, meaning their bodily balance, to react optimally and stay on the board without hesitation. Moving forward, we must cover several essential AI concepts you will inevitably encounter in enterprise environments. First are large language models, widely known as LLMs. These AI systems are trained on massive volumes of textual data and utilize a specialized neural network architecture called a transformer. A transformer heavily weighs the sequence and relation of inputs to deeply understand context and generate highly accurate, human-like text. Think of a professional speed reader who can grasp the entire plot of a chapter instantly by seeing how all the sentences connect structurally rather than reading it one isolated word at a time. Next, we have prompts. A prompt is the human-generated input used to initiate an output from a generative AI system. A poor, useless output is almost always the result of a vague prompt, not a technically broken model. It is exactly like jumping into a taxicab. If you just vaguely tell the driver to take you somewhere fun, you might end up somewhere you hate. You must provide exact GPS coordinates to get the specific geographic result you want. Then there are foundation models, frequently referred to as general-purpose AI. These foundational models are trained on incredibly broad, expansive datasets, allowing them to be easily adapted for dozens of completely different tasks, from generating original artwork to discovering new pharmaceutical drugs. A foundation model is like an Olympic decathlete. Their baseline physical conditioning is so incredibly broad and robust that they can successfully adapt to run, jump, or throw, depending entirely on the current event. You must also understand natural language processing, or NLP. This is the specific AI branch combining computational linguistics, deep learning, and machine learning to let computers accurately interpret and generate human language. It processes spoken audio commands and text documents, acting exactly like a bilingual diplomat, translating messy human intentions into structured, binary data a computer can actually execute. One of the most critical enterprise uses of NLP is sentiment analysis, which is also known as opinion mining. This analyzes massive volumes of text data to determine if the emotional sentiment is positive, negative, or neutral. In audit and data science, this classification is officially called polarity. It can be built on simple, rule-based systems or advanced machine learning. Think of it as an automated traffic light system for a corporate brand manager, immediately flashing green for glowing customer reviews and instantly flashing red the second a customer posts a furious complaint online. We conclude this technical section with two critical training risks that auditors must actively monitor and test for: underfitting and overfitting. Underfitting occurs when a model is far too simplistic to capture the underlying patterns in the training data. It performs terribly during both the initial training phase and the final testing phase, resulting in heavily biased and entirely inaccurate predictions. Imagine trying to wear a generic, one-size-fits-all suit to a formal corporate event. Because it lacks any detailed tailoring or structure, it fits terribly in every possible situation. Overfitting is the exact opposite issue. This happens when a model learns the training data too precisely, literally memorizing random noise, mathematical errors, and strange outliers. The model performs flawlessly during control training, but completely falls apart when presented with new, real-world data. Imagine getting a suit tailored so incredibly tightly to one specific standing pose that the moment you try to actually walk across the room, the seams instantly rip apart. As an auditor, you must ensure data science teams have robust validation processes to catch both underfitting and overfitting before an AI system is ever approved for production deployment. Let us recap the critical takeaways from this session. We defined algorithms as the mathematical instructions processing data governed tightly by human-adjusted hyperparameters. We thoroughly reviewed supervised models that rely on labeled data and unsupervised models that independently find structure through clustering and component analysis. We explored the trial and error reward mechanisms of reinforcement learning. Finally, we defined crucial enterprise AI terms like transformers, NLP, opinion polarity, and the massive deployment risks associated with poor model fitting. To ensure you are totally prepared for the exam, your next step is straightforward. All the important topics, audit risks, and complex terminology from this session are covered in the rigorous multiple choice questions on RooCloud.com. You should absolutely log in and solve the chapter-wise questions right now to reinforce your understanding of these algorithmic concepts before we tackle the next module. Thank you for your dedication, and I will see you in the next episode.